Hello world, it's Siraj, and today I want to talk about defense against adversarial attacks. This is one of those parts of machine learning that I haven't really talked about before, but as I was doing research for this video, I was surprised because this stuff is super interesting. It's basically a collection of really clever techniques by both attackers and by defenders on how to either break into these systems or defend them against attacks. So in this video, I'm going to start off by showing you this web demo right here that you can run in your browser. It's called advis.js. I found it on GitHub by Jack Spall, and you can install and run it easily with clone, yarn start, or you could run it in the browser. I love it when these GitHub demos have a web component to them. And you could try them out yourself. So basically the idea here is that, first of all, I'm gonna show you two types of attacks and then two types of defenses. The first type of attack, let me see if I can say it correctly. It's called the fast gradient sign method, FGCSM. And then there's the second type of attack, which is called the backwards pass differentiable method, or like backward pass differentiable approximation. Those are the two types of attacks. They're both really interesting mathematically and in terms of code, which I'm gonna show you. But this method right here that I'm gonna first demo for you in the browser is the fast gradient sign method. Basically, the idea here is that we have a classifier. It's an image classifier. You know, it just will classify any image as panda or whatever label that it's been trained on. And what we can do is we can give it a new image that is slightly transformed, just a little bit. It's almost as if it's not gonna be even noticeable to the human eye. So we'll take this original panda image that was correctly classified and we'll just slightly transform it a little bit. And what that's gonna do is, as you can see here, it's going to totally misclassify it as a chihuahua, even though it's a panda. And you might be thinking, well, how is that possible? Like, it's clearly a panda, just a small transformation and it totally misclassified? Yes, that is the case. And that's why this theory is super interesting, because we all need to know about how this works. I'm gonna show you how this works, by the way. I want you to go to this website, glin.xyz/advis, play around with this. So you don't even have to install it on your local machine. You could just run it in the browser. I'm gonna give you a more detailed explanation of what adversarial attacks really are in terms of the data distribution. And then we're gonna talk about the first attack vector, the fast gradient sign method, then adversarial training, the first type of defense, and then the better attack method, backward pass differentiable approximation, and then the better, most state-of-the-art current mode of defense, which is by NVIDIA research, which is called the barrage of random transforms. Really, really clever idea by the team at NVIDIA. Anyway, so here's the idea behind adversarial attacks. We have two different classes of data, for example, in this case, right? So we have red and blue. And when we plot all those data points on a two-dimensional graph, we'll find that, okay, these are clearly segmented and clustered into two distinct regions. Okay, so let's say we want to build a classifier here. And so a classifier in the case of this collection of data points would be a straight line that separates the blue and the red, right? Okay, so that's what we'll do. So let's say we build that classifier, and lo and behold, there it is. Now we have our classifier. Now, how would we fool this classifier so that if we give it a new image, let's say a red image, it's actually a red image, we will just change it, transform it like we did in that web demo, ever so slightly, so that the classifier will think, oh, this is a blue image for sure. How would we do that? So the way to do that is to say that we are going to slightly transform a red image in the direction of the blue image, such that the machine will think that it's a blue image. And so what happens is this epsilon parameter, we call it epsilon, is basically like a little tuning knob. And we literally saw that tuning knob right here. It's literally a sliding scale knob. The more we increase that epsilon value, the more transformed that image is going to be into some kind of panda lookalike, or in this case, red lookalike, blue lookalike, even though it's red. Okay, so there's so much to explain here. I'm super excited. I understand how this works, so I want to explain it really well. When I say that we transform a red data point into a blue data point by using the direction of the blueness, that is a gradient value, and that is how we get to the fast gradient sign method, which I have to talk about. Like I was gonna show you the demo first, but now I realize like actually I need to explain how this works. So here is the math equation. Just take a look at this first math equation. I basically just copied and pasted a few different versions of the equation so that you get a more generalized representation. But basically this image, this code sample, this image, and this image, they're basically all saying the same thing. This is how the fast gradient sign method works. And the idea is that we have our original image, which is X, right? That's the original input data point. And we want to create X adversarial. That is the fake X, which is going to be misclassified. How do we do that? Well, we take the original X input image, which is basically a collection of numbers, and then we add epsilon time, epsilon is that number that we can increase or decrease, times the sign of the gradient. Okay, so this right here is the gradient. So let's talk about that. So what happens during the backpropagation, during the learning process, as this classifier is being trained, what's happening is we are computing the loss with respect to the weights. Basically, let me say this very, very well. So during the training process, as we build this classifier, the classifier is going to, during every iteration of the training loop, as it's getting better and better at classification, it's making predictions. And it's saying, oh, this image right here, it's probably a blue image. And then the reality of that image, the label will say, oh, it is a blue image, you're right. Or it's, no, you're wrong, it's a red image. Now, whatever the true label is, it will compare that against the predicted label. In this case, it's blue or red or whatever it predicted. And there's a way of measuring how bad that prediction is. And that is the cost function, also called the loss function. We can use that cost function to approximate how we should tune those weight values such that the next iteration, that prediction will be even better. And this is by using gradient descent. And I will not explain how gradient descent works again, just because I made that a personal rule after making at least like 15 videos in depth. Just search gradient descent Siraj if you want a good video on that. But basically the idea I'm trying to convey here, high level, is that we use that cost function to approximate a gradient, a single collection of values that will allow us to update those weight matrices so that it's better. This gradient tells our classifier in which direction to improve over time so that it keeps classifying better and better. This gradient can also help our attacker. Instead of telling the classifier in which direction to learn to better approximate the function it's trying to learn, we can use that gradient to create an image that is transformed in the direction of a misclassified image. So basically, the classifier is going to keep outputting these gradients while it's training to improve itself. We can take that gradient and say, oh, this is the direction you want to draw the line so that the boundary between red and blue is as such. Okay, that's the direction. Let me take that direction vector and apply it to an image that makes you also think this red image is a blue. Oh, it's not. Oh, let me just transform it so you think it is. So basically what it's doing is it's transforming the numbers, the pixel values in that image such that the classifier will also think that it's moving in the direction of the wrong class, just like how it's updating its own self during training as a classifier. You see what I'm saying? So we can actually look at this code example right here, which does the same thing, right? So this model will make a prediction about the data point X, okay? And then it's going to subtract it from the true label. So that's the cost function. And then we can say, okay, so multiply that derivative value by the model's weight value. It's a matrix multiplication. And then apply this sign function to it, and that gives us a direction. And we can take that direction and apply it in this last expression, which is basically the same as this expression right here, x plus epsilon times the direction of wherever this classifier is training. And that it will transform that initial image such that it will become easily misclassified, unless there is some kind of defense mechanism there for the attack vector. Okay, so that's the idea behind the fast gradient method. You have a panda image, for example, plus epsilon times the gradient value. So it's It's not random noise. It is noise, it's just not random noise whose direction is in the same as the gradient of the cost function with respect to the data. And that's gonna give us, to us it looks like a normal panda, but inside the numbers, the pixel values, that's what's being duped here by this, okay? So you might be thinking, is this just good for images? Yes, it is good for images, but it's good for a lot of different use cases. Computer vision is everywhere. It's in facial recognition technology. It's in self-driving cars. There's actually a paper that says that you can change the speed limit of a sign if you hack into a car's onboard camera. And so the car itself will go way faster than it should. You know, instead of 40, it'll go 500, whatever your metric system is. Biometric recognition, text applications use convolutional networks as well. Think CNNs for sentiment analysis or text classification. Ad blockers can incorrectly classify ads. Spam classifiers can incorrectly identify malicious emails. So this applies to every single industry that uses convolutional networks, that uses any kind of image processing techniques. And actually, there are ways of doing this for text data, for numbers, for all sorts of data, but we're not going to go into the huge amount of theory there. We're just focused on images in this video because we want to limit it a little bit, all right? So that's the idea here. Now let's talk about this demo. That I think this is a really great demo to play with to learn more about this field. So what is it using? So first of all, it's using React. Now I love React. It is this beautiful front end template for these web apps that basically lets you create these components that will render the DOM in real time. There's this other idea of a virtual DOM, and React is super cool. It's super hot in the JS community. Basically, it lets you build front ends faster, and it lets you build them more efficiently, and it lets you crucially keep track of state, where state is, you know, has a user logged in or not? Have they purchased this product? Whatever their actions in the network are. And then of course, tensorflow.js, it uses that. Basically, you load an image up, there's a pre-trained classifier there, and then it will classify the image correctly. Then you can choose to add some sort of transformation to that image, and then it will classify it incorrectly. And it's using the fast gradient sign method that we just talked about. It's also using this beautiful thing called the CAM, the class activation mapping. Basically, when we have this convolutional network and we're feeding this image through each layer, we can actually, from one of those layers, the final global average pooling layer, we can take the class-specific gradient information and produce a localization map of the discriminative regions of that image. Basically, we can ask the network to tell us what parts of the image are the most important whenever you're making a classification. So in this case, because it classified as Australian Terrier, we can go back into the network, peer into the layer, and see a visualization that says, oh, this part is the Australian Terrier part. Now we can use that to help us debug the network over time and learn how to improve our training. Let's look at this. So we'll just go here and download this repository, open it up, and then we'll CD into it. And let's see what the deal is with this repository. So inside of the package.json, quite a lot of dependencies. Let's see, D3, great for visualization. Interesting. We've got some, you know, boilerplate scripts. D3, tensorflow.js, like I said, and then React and all of the React modules. Okay, so let's see what is in here that's useful. Okay, inside of the source folder, we have app.js. Okay, index, there's some React components. What do we really care about here? We care about model.js. Okay, so here's what's happening. Here, so they're using MobileNet as that default classifier in the browser. That's what's able to, you know, create these new attacks, increase the epsilon to whatever. Then you'll find the CAM difference versus the original, and it will know, okay, this is bad. This is a vulnerable classifier. That's why we're testing it. It doesn't have any defense. So this is the predict function, and inside of the predict function, we say, okay, here is the network, classify it, true or false. Great. Okay. Here are some of the adversarial hyperparameters. So what we do is we say, okay, get adversarial examples. Okay, how are we going to get those adversarial examples? Well, here is where they're generated, right here. So we create a series of perturbations or transformations, however you want to say it, using those gradients, like I said before. So this is the fast gradient sign method that I've been talking about. And we basically apply some transformations and then return that image. So this function is basically a nested function inside of this function. So this function creates a single image. This creates a collection of them. And then we try to get those classified by the classifier. That's how that works. And then inside of app.js, we see that rendering of all the div code, the virtual DOM is there. And then there's, what else we have? Do we have explanations.js? Interesting. Okay. I mean, there's quite a bit of here, but it's all very doable, useful code. Display, just UI elements right here. UI elements. App.js is interesting, but I think the most important JavaScript file for us is model.js because that's where the adversarial code is. That's what we want to learn from. Okay, so that's that. Now let's look at a defense. So how do we prevent this from happening? So this is just a super simple yet still ingenious idea. Basically, if we want to prevent that kind of adversarial attack, one of the first defenses, and this was suggested by Goodfellow, the author of Generative Adversarial Networks, a while ago, the way to prevent that from happening is to do it yourself and train your own classifier on those misclassified images with the wrong label. So basically what you do is you do this yourself. You create your own epsilon valued images that are totally going to be misclassified wrong. Take those wrongly classified labels, give it to them, and then train your model on that. So that given a new one, if someone gives you an epsilon 19 panda, guess what? You've already trained on an epsilon 19 panda or something similar, maybe epsilon 17. It'll still learn. And that is called adversarial training. The idea behind adversarial training is you just do it yourself so that you're going to be impervious to those types of attacks. And I've got a great example for you right here. So in this example, it's also a collab. I basically just started using Colab for like literally everything that I want to show because anyone can use it in the browser. You don't need to download anything or it's just super easy to use. So definitely check out this collab. But basically it uses PyTorch to show you an example of adversarial training or at least of adversarial generation. Anyway, the point is that it's creating a convolutional network. We've seen this. It's just the same, convolutional network. It's creating a data set. Great. MNIST, those handwritten digits with the labels. Great. Initialize it, load it, evaluate it. Great. Here is the attack code right here. So this is the code in PyTorch. We just showed it in NumPy. Here it is in PyTorch. We have that image, the gradient, and the epsilon value. Those are the three inputs to this function, which will return that transformed image. Take the gradient, element-wise sign it, which is basically you get more of the essence of the gradient by doing that. Create that transformed image by adjusting each pixel of the input image using the gradient. There it is. Add clippings to make sure that it's formatted and return it. Now this function right here is used during the testing phase right here to see if it was classified correctly or not. We could easily put this function in the training phase as well, and that makes this an adversarial training procedure. But in this code, it just adds it to the testing case, which is fine. But I just want you to know that it's easily modifiable to make this an adversarial training example. Okay, so now let's talk about the second type of attack, which is called the backward pass differentiable approximation method, BPDA. So the way this works is, first of all, the fast gradient sign method, it works okay, but we just talked about that defense of adversarial training where you could just train it on similar images. So attackers are smart. They understand that it's a cat and mouse game that you're playing with a defender. The gradient is really that key value that they need to create this transformed adversarial image, correct? What if we could take that gradient and make our own network using it? Right? So they basically decided that if these defenders are going to try to mask the gradient by using, various masking techniques, privacy, encryption, maybe they might just not even use gradients by using a non-differentiable method, usually with decision trees or some non-differentiable method where there is no gradient. Well, there's nothing to steal then, right? The way to get around that is this is just ingenious. Basically, the way to get around that is to rebuild the network from scratch. If you can't approximate f of x, where f of x is the network that you're trying to break into, create a new network called g of x, train it on the same images as f of x has been trained on, and then use your own gradients. If you can't take their gradients, make your own gradients, right? So that's the idea behind BPDA. So just recreate the network yourself. Now, this image is extremely dense, to say the least, but I just wanted to show it to you because I thought this was super cool. Somebody's notes here about obfuscated gradients give a false sense of security. It's pretty interesting to find an image like this. I've never seen anything like this. It's like a map of a very specific part of machine learning. So props to whoever made this. And I think you should just look at this at some point in detail to give you some idea of where this person's headspace was at. But right, the idea is that we just create a new network called g of x that approximates f of x. You don't even have to worry about gradient masking because you'll just make the network yourself, trained on the same examples as that other network. And then here I found this great example. It's called AdverTorch. So the idea behind AdverTorch is it's basically a version of PyTorch that is suited for adversarial training and adversarial testing, where you'll find this method is used, where is it used in AdverTorch? These are all newer libraries. All these adversarial libraries are super new, right here. So they've already got BPDA as its own function. We just implement it with a single line using the current model as a way of copying from the current model, and then running it on the MNIST dataset right there. So also, I want to say this as well. So if we're on the topic of great libraries for adversarial training, I can't not mention CleverHans. So CleverHans is by the TensorFlow team, I think. Yeah, it is, because it's in their repository. And basically, it's a way to train your model on all these adversarial examples. So what I want to do is I want to show you all of their different types of attacks that they have in here built in that you can use as a starting point. So check this out. In their documentation, they have this attacks module, which basically encapsulates and implements a bunch of attack methods that you can test on your own model. So rather than copying, rather than just like typing them all out yourself, you can use CleverHans to try to see how good your model fares against the elastic net method or fast feature adversaries, all these different methods. So definitely check out CleverHans. So that's that for AdverTorch, for CleverHans, and for that second attack, backward path differentiable approximation. How could you possibly defend against that? Well, the team at NVIDIA created this genius strategy called the barrage of random transforms, or BART. Who would have thought BART would save the day? But whatever. So the idea is that, okay, if you have a bunch of these weak defenses, like a slight transformation, you can just build an adversarial training defense against that. Or if you mask the gradients, well, they'll just create a new network. Well, what do we do then as an attacker? And then we'll look from the point of view of a defender. From an attacker, we could just say, okay, we'll make a new network, or we'll perform adversarial training on our own copied G of X network. The way to defend against all of that is to, instead of having a single weak transformation that we saw here, epsilon, that we're just applying, let's have multiple. In fact, let's have a barrage of them, lots of different types of transformations. Color precision reduction, noise injection, fast Fourier transform perturbation. Okay, so all of these different types of transformations. And the key here, that's the key, but another key here is to try these randomly. So when you try them randomly, the attacker won't know which one that you're training your model with. So whenever you're training your own model, just basically have it train on a bunch of different transformed images, and that way your model will be robust against adversarial attacks that are trying to replicate your own transformations. And also, because these transformations are applied randomly, it's hard for this attacker who's trying to recreate your model, G of X, to try to predict which transformations you're going to apply to which data points, because they're random, right? So because they're random, you're protected against both types of attacks, the fast gradient sign method and the backward pass differentiable approximation. Now, this is a super new method, by the way. Like they basically just kind of released this. So there is no associated code for this yet. I mean, this was just released, I think a few months ago, definitely this year. What we can do is we can see like what this looks like visually. It's kind of trippy, but this is the barrage of random transformations. And they just wanted to show it as a video by showing them in order, the collection of frames. Here's the paper. I really wanted there to be code, but there's not code, but that's okay. I'm sure they're gonna release it very soon. So this is the paper if you want to read it. But even though there's no code available for this one, I found something that's pretty similar. You know, it's kind of similar. So this is a 2-year-old example. But basically, this paper proposed to improve the transferability of adversarial examples by creating diverse input patterns. So it's kind of similar in that it's using a bunch of random transformations to the input images at each iteration, and it's using these different techniques to create them. Remember, you can use the same attack techniques to create the same defense techniques. It's this cat and mouse game. And this is a great repository to try to learn more about it. If we look under attack.py, luckily it's pretty clean code right here. We have the graph, input diversity. So right here, right? So they always use these matrix libraries. They're using TensorFlow in this case to create those random transformations. So this is the function to look at, input diversity, which creates them. Okay, so yeah, so that's it for that second defense. We basically went over in this video 2 types of attacks, the fast gradient sign method and the backwards pass differentiable approximation. And then we went over 2 types of defenses. We went over adversarial training, and then we went over probably the state-of-the-art technique right now, which is the barrage of random transforms. Now, adversarial machine learning is a super exciting field. Security is only going to become more important over the years. So definitely take some time to look into this collab that I've created. Take some time to look into the examples that I've demoed to you, and just take some time to learn about this. This is a super exciting field with a lot of opportunities in machine learning. So I hope this video was helpful for you.